All right, so we're going to pick up here after you have watched
So we
your
looked at
video
ultrafiltration.
You have water passing through a barrier with
My
holes,
pen set up again.
and the water can pass through the holes and the impurities cannot. And depending on the pore size, some compounds go through or not. So here's a diagram from your text that shows how this filtration takes place. You have water under pressure entering a tube with pores. And so here you have a pore size that will block certain large bacteria and also colloids, those larger particles, but allow the water plus all this other stuff to get through. And as you decrease the size of the pores, then you start to eliminate smaller and smaller items. So you have viruses getting excluded. They're smaller than bacteria. And then you have some of the larger cations that can be filtered on this size scale. And then here you have the smaller cations. And so here's a summary of those. 0.1 microns for bacteria and colloids, 0.01 microns for viruses. Here you have, this is on the order of a nanometer, and here we have a fraction of a nanometer. So depending on your pore size, you can filter different components. This process is reverse osmosis. So you're putting pressure on the concentrated side in order to push the purified water out. And so this is kind of another way of representing the same thing, where you have, if you have a pore size, the size of this blue, then you're going to filter out the bacteria. And as you get smaller and smaller, so the red corresponds to being able to filter out viruses. The yellow size, here we have 0.01 micron pore. Get smaller and smaller. Here we can start getting it calcium carbonate filtered out. By the time you're in here at a fraction of a nanometer, you can start filtering out sea salt. And this is interesting because it can be used then for desalinization. Desalinization, it might be desalination. That sound better, yeah. And this is actually used in places where they have access to salt water but not fresh water. You can use reverse osmosis to purify that. And here's another schematic representation. When you have larger pore size, you have more components that can pass through. Smaller pore size means only the water gets through and the ions are rejected. So advantages and disadvantages of using this reverse osmosis. So first of all, you probably think of the main advantage here is that you get extremely pure water. The purity is going to be limited by the size of your pores. And so if you have a very fine pore filter, then yeah, you're going to get very pure water. And it can also be used for desalination. There, that's pretty close to how you spell that. Disadvantages of RO water. First of all, it is energy intensive. Okay, so you have to create this high pressure environment to force the water through the filter. And you also have to create the filters as well, produce those. It's also wasteful of water. As much as 1/3 to 1/2 of the total water has to be thrown out. This is because after you have applied pressure to it, you have pure water on one side, you still have the impure water on the other side, and that impure water needs to be disposed of. And another sort of disadvantage here would be that the water needs to be pre-treated. So it needs initial filtering and other treatments to get out the largest particles, because if you start putting really large colloids and things into a very fine filter, you're going to foul your filter more easily. And so in order to preserve that filter, you need to do a number of treatment steps before you even get to the reverse osmosis. So more steps means more time, more expense. Can you drink it? What do you think? Well, maybe a little, but in general, drinking too much will upset your ion balance. So you need to be consuming ions in your water in order for your body to do what it does. You don't want to start having this hypotonic situation in your cells. All right, so let's look at ultraviolet radiation as a way to purify water. Just going to do a little reminder here of our electromagnetic spectrum. Let's see, here's the visible light in here that we can see. Down here is infrared, right? And so in the infrared, this radiation interacts with molecules and causes them to vibrate. And let's see, down here, microwaves and radiation. This is where electrons will oscillate. At the high energy side of things, ultraviolet causes bonds to break. And up here, X-rays and gamma rays, you have ionization. So just across the spectrum, this is how the radiation interacts with with matter. In the case of using radiation to disinfect water, we're going to be looking at the ultraviolet. Okay, we're here in the bond breaking regime. UVC radiation is in the range of 254 nanometers. And if you expose the water at this frequency for 10 seconds, this will kill microorganisms. It disrupts the bonding in their DNA, basically makes them unable to continue living. So yeah, UV radiation, it's a great way. If you can ensure this exposure time at this wavelength, then you're going to kill everything that's in there. But there are complicating factors. So, say complications. What do you think those could be? What could interfere with this UV process? First of all, you can have other absorbers. So if you have other molecules absorbing this UV radiation, it's not getting to the microorganisms. It may not completely kill them. This includes iron and also organic molecules. Another complication would be scattering. If you have colloids or other things in the water, then the radiation will be reflected away or scattered off, and then it won't be available to kill the microorganisms. An advantage of using UV radiation is that it can happen on a small scale. And so you can have, a household size UV radiator on your faucet that could kill things. So you don't need to have a centralized water treatment facility for this. It could be decentralized. Decentralized treatment. All right, let's move on then. All right, so we're going to use oxidation to help purify our water, and O2 is not strong enough to oxidize bacteria and viruses. So we're going to talk about using ozone or chlorine dioxide. I'm going to change my pen color back here. All right. Okay, so first let's talk about ozone. Ozone has a short lifetime. So it can't be stored or shipped. It needs to be produced on site. And they do that using an electric discharge in air. And when you, it's like a giant lightning bolt, you hit O2 and you break it up into 2 O atoms. These O atoms can then react with oxygen to give ozone. And this ozone is very reactive. It will react with pretty much anything it collides with. This is what makes it useful as an oxidizer in water. It also has some complications. So let's see. So complications of using ozone would be this short lifetime. So you don't get any residual protection. So the ozone can, kill the bacteria and viruses that are present at the moment of treatment, but as the water flows down the pipe, it does not carry with it any residual protection. It also has the complications of side reactions. And these can produce products like formaldehyde, which is toxic, and bromate, which is carcinogenic. So depending on what chemicals are present in the water before treatment, you can get these products from, these are from organics, and these would be from halogens. So these are disinfection byproducts, DBPs. And all chemical processes produce these. About the chlorine dioxide. Okay, so this was ozone, and then let's start by drawing a Lewis structure for chlorine dioxide. We'll put the chlorine in the center, and here are the 2 O atoms. How many valence electrons do we have? For chlorine, we have 7. And oxygen gives us 6. And there's 2 atoms, and so we get a total of 19. And this you can see is already interesting because it's an odd number. Okay, so let's fill in our 19 electrons. We'll put 2 here for a bond, and then here's 4, 6, 8, 10, 12, 14, 16, 18, 19, right there. We have an unpaired electron. Which means this is a free radical. Free radicals love to collect electrons. Okay, so here we have our chlorine dioxide, free radical. In an acid environment, will pick up 5 electrons, and we'll end up with chloride and water. All right, so where do these electrons come from? If you remember back a week or 2 ago, we talked about these organic molecules. So we have an organic something or other that is going to give up its electrons. we now have an organic cation and an electron. Then this organic cation will react with O2 to give us CO2, water. So now our organic contaminants have been converted into carbon dioxide gas and effectively removed from the water. So this chlorine dioxide is an oxidizer, but it's not a chlorinator. Okay, it contains chlorine, but the chlorine itself is not what is purifying the water. And I think I will stop there, and we will start talking about chlorination next time in class. I will see you then.